That's really important. Good evening. I'd love to invite you all to take a seat, and in 1 minute, I'll open up the program. Well, good evening. Welcome. And we're so glad to have you with us tonight for our 10th annual V. Elving Anderson Lecture in Science and Religion. My name is Casey Shalopsky, and I'm the Associate Director of our Center for Faith and Learning here at Anselm House. So Anselm House has been present on this campus at the University of Minnesota since 1982. And our mission is to connect the Christian faith with all areas of learning at the university. And we do this because we humbly contend that when we properly align faith and reason, the result is an approach to God, to our neighbors, and to ourselves that yields truth, goodness, and beauty. So we sponsor events and nurture a community conducive to this end. Please know that whether you are joining us for the first time tonight, if you have some community for many years, whatever perspective or background you bring to tonight's topic, we are very delighted to have you with us and part of this conversation. In the fall of 2022, we moved into our new physical home, Melrose Station, which is just right across the street on Washington. And we have settled very nicely into our new study center and encourage any of you, especially if you're student, faculty, or staff at the university, to stop by and see our place. We've also been busy creating a new institutional home for our academic engagement programs, a Center for Faith and Learning within Anselm House. This Center for Faith and Learning's particular focus within the broader Anselm House mission of connecting faith and knowledge with all of life is to support the University of Minnesota's academic community in asking the big questions of ultimate meaning and purpose. The center functions as a convener of important disciplinary and interdisciplinary conversations among faculty, academic staff, and graduate students here at the U. This evening, we continue a series of annual lectures focused on the relationship of Christian faith to the natural sciences. Our Anderson lectures are named in honor of V. Elving Anderson, a distinguished geneticist here at the University of Minnesota, a committed Christian, a national leader in faith and science conversations, and a key early faculty leader of the McLaurin Institute, which later became Anselm House. And we're delighted to have Dr. Carl Anderson, son of Elving and Carol Anderson, joining us for tonight's lecture. Carl, we're very happy that you are here with us tonight. These Anderson lectures have featured some of the most distinguished Christians in the sciences, speaking to the intersection of their faith with their academic work. Our past Anderson lectures have included climate scientist Katherine Hayhoe, physicist Stephen Barr, neuroscientist Bill Newsom, and last year, the Pope's astronomer, Brother Guy Consolmagno. For our 10th Anderson lecture, we're delighted to host Dr. Fred Skiff from the University of Iowa this evening on the topic Purposeful Beauty, Exploring the Mysteries of the Aurora. I'd now like to welcome my colleague and the director of our Center for Faith and Learning, Dr. A.J. Polerans, to introduce Dr. Skiff. Thank you.
Well, good evening, and thank you, Casey, for introducing the Anderson lecture and for all the work that you're doing. Without Casey's work, she is like the whiz, I would say the whiz kid, but that's not the exact language, so to say. She manages all of this kind of stuff and makes all of this possible. And thank you also to you all for being here tonight. My name is AJ Poularens. I direct the Center for Faith and Learning at the Anselm House. And I'm very excited to welcome all of you and to welcome Dr. Frederick Skiff, Professor of Physics at the University of Iowa. Dr. Skiff did his undergraduate work at Cornell University and received his PhD in physics from Princeton from 1985 till 1998. He was a research physicist at the Swiss Federal Technical Institute, after which he worked for about 10 years at the University of Maryland. And he has been at the University of Iowa since 1998. Did I flip those around those numbers? I don't remember. And he served as department chair of the physics department for many years as well. And he had some really good stories to share with us over dinner about those years as department chair. Dr. Skiff is an expert in plasma physics and laser spectroscopy. That might not mean anything to you yet, but plasma physics is pretty cool, or hot, whatever you prefer. Just as a starter, plasma makes up 99.9% of the visible universe. Plasma is often called the fourth state of matter, along with solid, liquid, and gas. And just as liquid will boil, changing into a gas when energy is added, heating a gas will form a plasma, a soup of positively and negatively charged particles that are interacting with each other or not interacting with each other. And when you look beyond the Earth, almost everything that you see in the universe is in the form of a plasma. So our sun, for example, is a plasma. All the other stars are plasmas, nebulae, and you can even describe the whole galaxy as kind of one big plasma thing. And our topic for tonight, the Aurora, are also plasmas. The Aurora, those mysterious, beautiful, wispy things that ripple above the North and the South Poles. Because so much of the universe is made of plasma, scientists are deeply interested in understanding and possibly also manipulating plasmas. For example, nuclear fusion, the process that powers stars, including our own sun, could potentially solve our energy problems, but only if we know how to control and how to manipulate plasmas and how to contain them within magnetic fields, because the conditions are so extreme. You basically try to mimic what happens inside of the sun itself or stars itself. But if we're able to do that, we are actually able to generate energy in a way that we've never been able to generate that. And the joke among physicists is always, it's still 50 years out. It's always 50 years out. So if you had asked people like 20, 30 years ago, like how long does it take before we're able to kind of really generate energy from plasmas and from nuclear fusion? It's about 50 years out. And that is still, maybe it's a little close, maybe 40 years, we'll see. There's some really big breakthroughs over the last couple of years that are very, very promising. Anyways, that's plasmas. So plasmas are very, very interesting, very, very important, and potentially could actually change our whole life. So understanding plasmas is Dr. Skiff's life work. In his work, he combines both experimental plasma research with theoretical work on plasma, such as kinetic theory, waves, and nonlinear fluctuations. And his lab is equipped with a 3-meter linear magnetized plasma device and also a large multipole discharge. But he also collaborates with researchers at UCLA on the large plasma device, which is even bigger than that thing. It's a really cool device. If you're into those kind of things, that is kind of something. In 2021, members of his lab published a groundbreaking paper explaining possibly the origins of the Northern Lights in Nature Communications under the beautiful title, Laboratory Measurements of the Physics of Auroral Electron Acceleration by Elving Waves. Now that doesn't say anything to you, but if you're in plasma, this is actually pretty cool. So I knew Dr. Skiff, and I know also one of his co-collaborators, who's a really good friend of mine and a former colleague of mine, who was the main author of that paper. Tonight, Fred will speak on some of that research, but he also will dive deeper into questions on what actually is science and how do we come to know something. Fred is an active member of his church in Iowa City. He's the faculty advisor to the Reformed University Fellowship in Iowa City at the University of Iowa. He's involved with the Geneva House, which is a Christian study center, similar to Anselm House, on the campus of the University of Iowa, and also a regular speaker on topics of science and faith and the interface of science and faith. So please join me in welcoming Dr. Fred Skiff for this 10th annual Anderson Lecture in Science and Religion.
Thanks, AJ. Yeah, it's a pleasure to be with you here today, and I just really enjoyed getting to know the Anselm House people, and I wish so much when I was a freshman in university that there was something like this on my campus. There is now, actually. Cornell campus does now have a Christian Studies Center, but they didn't back in the 70s. So, well, I just thought I did look at some of the other Anderson lectures, and I noticed that a lot of them started with a little video, so I'm going to start with a little tiny video clip. This is courtesy of NASA, and about the nature of auroras. So it'll just be a couple of minutes, but...
What is an aurora? An aurora is a brilliant display of light in the sky. These are similar to the skies, clouds, and the You can also see auroras from space. This is what an aurora looks like in the International Space Station. The naming of an aurora changes depending on its location. The northern hemisphere is called aurora borealis, aurora borealis. And if you're in the southern hemisphere, then it is called aurora australis, or southern lights. So, what causes these beautiful displays of light in the day? The sun. That's right. He knows auroras are glistening at night. These colorful displays are caused by our imagination of the sun. How does that happen? Well, the sun is constantly sending heat and light to the earth. It also sends particles and releases small electrified particles too. This is called solar wind. The magnetic field, which protects us from most solar winds, but it also traps some of the electrified particles in the space around Earth. The sun does not always send the same amount of energy. Sometimes the sun has huge outbursts and blasts more stuff into space than the usual solar wind. These events are called solar storms. During one kind of solar storm, called a coronal mass ejection, the sun burps a massive bubble of gas that pops and sends particles and energy zooming through space. When a solar storm reaches Earth, it dances with our magnetic field, and some of the energy and particles that zip around the magnetic field dive into our atmosphere near the north and south poles. The particles then bump into gases in our atmosphere. These interactions result in displays of light in the sky, auroras. When the particles bump into oxygen in our atmosphere, the reaction makes green and red light. When the particles bump into nitrogen in our atmosphere, it makes blue and purple light. Earth is not the only planet with auroras. If a planet has an atmosphere and a magnetic field, it probably has auroras. For example, NASA spacecraft have captured amazing auroras on Jupiter and Saturn. Learn more about our planet and our solar system at NASA Space Place.
So I gave a brief overview, and since when I talked to AJ, he said, well, this should be personal and show the integration, how integrate life and faith and knowledge. And so for me, I started in a situation which was, I would say, not integrated at all. I didn't have the privilege of being in a Christian home, and so I remember my father actually telling me that God didn't exist. And even though I feared him and didn't say anything back, I did ask questions, as little kids are prone to do. and respectfully asked him a couple of questions because I grew up in a log cabin in the woods in upstate New York, and I was very aware of the natural world around me and the beauty of it. And there were two questions I asked. One was, we had an apple orchard we had a small orchard near the log cabin, and I loved the apple trees because I could climb them. I used to climb the apple tree, and my brother would have a baseball catching mitt, and I would throw the really good ones down to him to catch, and then we'd shake the tree and make applesauce and things. And in the springtime, you had these beautiful blossoms, and it was great for our honeybees. We also had hives and things. And I asked my father, "Did you invent the apple tree?" I was like, this tree is just fantastic, and all I have to do is I can reach out and I get food. And it's, I had a concept of, it just seemed ridiculous to me, even as a little kid, the idea that this happened for absolutely no reason. And the other thing I love to do is we made ponds. The region where I grew up was wetlands, and wetlands are teeming with life. And in the shallow ponds, I would love to watch the tadpoles, and as you went out there from day to day, you'd see them metamorphose, right? And I thought, this is high-tech beyond belief. I mean, I didn't have the word high-tech, but for me, it was amazing beyond belief, this thing. And to think that these things could happen for no reason just made no sense to me at all. And, but my father did encourage my interest in science. But I must say that in 1967, at the age of 10, I was out camping in the woods, and we had a lot of woods that went up eventually to the Hudson River. And I was camping, and I loved to camp without a tent or anything, just beneath the stars. And an event happened. No one had ever told me there was such a thing as an aurora. I had no idea. Well, in 1967, there was a major event, and the aurora, not only did we have an aurora, it was so bright it looked like daylight. It was a really astounding event. You can go look it up on the web. And you could see it much further south than normally. Normally, where I was in New York, I was 10 years old, never heard of it. But, and it just totally astounded me, and I was wondering, is the planet blowing up or something? So it definitely piqued my interest and I eventually, towards the end of elementary school, I taught myself how to repair TVs and radios, and I had my own radio station, ham radio, and it was very sensitive to the solar cycle, the transmission, particularly at the certain wavelengths. So that really was my start. I was told that there was no God, but it didn't make sense to me at all. And so I went off to university. I went to Cornell, which was actually Israel Cornell was considered like the atheist of the Ivy Leagues, in a way. But nevertheless, I did study science, and my study of science actually is intertwined with my study of search and faith. So I became, those days, at least for me as a kid, one of the biggest things that was happening was, of course, landing on the moon and the new perspective we had on our own planet. And, one of the things as you study astronomy, which I started doing, is that most of the solar system, the universe, as far as we know, is not very friendly to life. It's, rocks, there's radiation that'll kill you instantly. And the Earth seen from space, it just is a beautiful garden. It's not only a place for us to live, it's magnificently beautiful. And so this connection between, the beauty and knowledge about, how does science work? For me, we're connected right from the start. So I went off and I learned, physics and went into plasma physics. So I'll give you a brief overview. because it's part of my personal story. And I realized that what AJ was saying is that most of the universe is, that we can see anyway, is ionized gas. And now you can see in the center here, what this graph is showing here is that temperature, and as AJ said, of course, it has to get hot, and those are measured in Kelvin, so right at the very bottom, it's almost down to room temperature, but not really, and then it goes up orders of magnitude, so powers of 10, up to 100 million degrees, which is the temperature inside fusion experiments, and then on the horizontal axis is density, which you can see covers huge ranges from the density inside stars to the density of the aurora. So the aurora density and temperature are, you can see in the lower left-hand corner. But it was a fascinating story for me. And of course, at the same time as it being interesting science and related to natural phenomenon, there are hundreds of very large industries which most people don't even know exist, or that plasma is involved in them. And one is that all the semiconductor manufacturing, for all the chips, it's all done with ionized gas, because you can't use wet chemicals to make things in really microscopic scale. It's been found that plasmas can actually help kill bacteria. There's a pen there, a plasma pen, and at a recent conference, usually at physics conferences, we don't have terribly difficult pictures to look at, but they had this picture of someone with a terrible, incurable skin problem, and they exposed the patient to plasma, right, at atmospheric jet like that, and it healed them, and nobody knows why. So there's a huge amount of ongoing research about how does this work, affects agriculture, the yield of seeds, and and of course, so if you want to go to Mars and come back, you need a better engine than we currently make. And so ionized gases can make propulsion. And so this is a plasma thruster. Fusion energy, so I did my PhD at the Princeton Plasma Physics Lab. And they're very much at the center of the fusion program there. And yeah, it's an extremely difficult problem, and there's much more physics involved than people realized at first, which is why I kept going 50 more years out. Now there's a lot of private investment in fusion, so we'll see. I still think it's full of surprises, so it could be more difficult than it appears. But there's one thing for sure: people are seeing fusion reactions, and fusion energy is a reality. Now the question is, can you make it competitive and safe? And of course, in my career, I've also looked at natural phenomena, and AJ mentioned this paper. So you have here at the university, you have excellent plasma research going on in two totally different areas. One is in mechanical engineering. There are people looking at these low temperature plasmas, like the kind used in semiconductor manufacture, and in the plasma thruster and things like that. And then there also is in the physics department, I gave a seminar this afternoon, they build instruments that go into space and make measurements. So you have actually some very first-rate plasma research going on here at the university. And not every university has that, I'll say. So it's practical, it's helpful. There are ways of, one of my motivations for going into physics was that I wanted to be able to do things that would help people. And the hope of fusion energy was, well, this could be a clean energy source, and then people have a choice about how they generate electricity. And even understanding our environment. Now, you usually think of, if you worry about the Earth's environment, you just study the planet Earth. But actually, the Earth's environment is strongly influenced by the sun in a number of ways. And one of them has to do with just with the solar wind and with its interaction with our atmosphere at various levels, magnetosphere, ionosphere, stratosphere. And a lot of those connections are only recently being understood or looked at, that the connection used to be there were scientists who specialized at different heights in the atmosphere, and they hardly communicated with each other. And so there's now actually integration in plasma in the sense that it's connected all the different layers of the atmosphere of the Earth and connecting all the way to the sun. So, and this affects, I mean, if we are in a period now, so the sun goes through cycles of activity, 11 years, really a 22-year cycle, which where the sun becomes very active, which means there's a lot of those explosions which were in the little video taking place. And solar maximum, actually, the next solar maximum is next year. And so you should be on the lookout. If you want to see an aurora, the next year is actually going to be potentially a good time to see it. And you have to, and there are announcements that NASA makes, because you have a little bit of time when those explosions happen. The particles leave the sun at a few million miles an hour, and it takes a little while to get here. So there's time enough to tell people, hey, there's probably going to be an auroral event, and you might be able to see it. So you have a little bit of warning. And there are many kinds of aurora, and so I'll just talk about a little bit about the one that we studied. And my role, although at Iowa, actually, I always have to say this since I was department chair at one point, the space program of the United States started at Iowa, and with James Van Allen in 1958, but we're still very involved with that. My work is actually in the laboratory. So I study phenomena which happen in space, but then produce a controlled environment in the laboratory, and then study those phenomena in a way that we can use precise measurements like laser spectroscopy and other things. Okay. But the other thing is that not only is the aurora beautiful, and not only is it, actually it's a kind of laboratory to teach us about physics, it makes life possible. I mean, the reason we have the aurora where we have it, little rings around the poles of the Earth, is the Earth is protected by a force field. A force field that we wouldn't, we'd be hard pressed to defend our planet without this force field. And, one of the things that's ongoing is the study of what would happen to our atmosphere if we didn't have the force field. And there are, it definitely would be different. And we have the case study of Mars, which does not have a magnetic force field and has lost its atmosphere. So one of the things that we do with plasma physics is write big computer codes that simulate. This is a movie simulating. So the magnetic field around the Earth produces what's called the magnetosphere. It's this area, and you can see though that those lines are magnetic field lines, and they've been pushed because there's a wind called the solar wind blowing from the sun that blows past the Earth and distorts that magnetic field. Yet that field there, you can see it's protecting the Earth, but yet there are little tiny wedge-shaped areas above and below where it looks like stuff can get in, and stuff does get in. And this is one way that auroras, are produced. Actually, if you go up to Fairbanks, Alaska, you can almost every night see the sky just glowing with a diffuse glow. And that is an aurora-like phenomenon. So that's not the one that we were trying to understand. The one we were trying to understand has to do with storms. So there's space weather, and it affects our satellites and everything. But to get to that place, I want to first now do a little bit of digression, because as I started doing this, I was greatly distressed when, I went to very good universities, and the faculty were very good, but everything was very specialized. So you can become a PhD, at an Ivy League school or any school, and nowadays, and never have thought about, well, what is the nature of science itself? What can you explain with science and what can you not explain with science? That's never discussed. What you're told is, well, you want to study this, well then, electromagnetism, well, you study electricity and magnetism, and so education tends to be very compartmentalized, and in fact, a physics student is often discouraged from philosophy, as if the humanities are not a worthwhile thing to do. Not everyone feels that way, but I certainly experienced that attitude going through. So I, on my own, insisted on reading. And my grandfather, who was not a Christian, said, well, if you want to be educated, you should read. And he told me, the various great books, Plato's Republic, and he had the Bible on that list. And I read it, and it was the first book I'd read where it was not at all what I was expecting, because I'd only heard negative things about it and about the church, in my childhood. And so I was surprised, because I said, wait a minute, this book is a perfect explanation for the human condition. This makes a lot of sense. And so I started to try to understand, well, for myself. And so this diagram I have up here is not something that I got in a lecture. It's my own observation of, well, how do scientists function? I got to work with some very well-known and very accomplished scientists. And so I tried to understand, well, how does science, even as a community, function? And so you see in this picture, and I won't have time to go through everything, but I'll just give an outline of some. I actually use this when I'm teaching advanced laboratory physics majors about the nature of science, because I think they should see it. They should think about it. So and I think for me as a Christian in the university, I just try to get students thinking and asking questions, and that actually is the best way to help them, also spiritually. So you have this belief in reality, objective reality. And, in our day and age, I think it's become a little bit unpopular to think of objective reality, but I've never met a scientist who didn't believe that they were studying something real. And it's interesting, I noticed as a student that there are things that they never teach, but I could see extremely helpful. One is wonder. The best scientists were fascinated by what they were doing. They weren't just coming to work and punching a clock. If you're smart, you can make money a lot easier than any other way than being a scientist. It's a lot of work. And so, why do it? Well, you love it because it's interesting. And so there's wonder. So there's no room for cynicism. And I would say I could make a whole long list of other virtues that seem to be really helpful if you want to be successful doing science. For example, humility. It's not taught in any class, but the fact is that if you're an arrogant know-it-all, well, then you've stopped learning. So you're useless to the scientific community. If you're humble and are very quick to admit where you don't. In fact, the best scientists are the first to raise their hand and say, you know what, I really don't understand this. And that impressed me. They were willing to be vulnerable and to admit that reality seems to be a lot bigger and more interesting than we had in mind. So this diagram shows that science is an interaction of experiment and theory. And I guess a little bit unusual in that I do a little bit of both. But the point is, there are a lot of assumptions here. And there are people, and the word materialism has been raised, and materialism is really the state religion that nobody admits. And it's certainly in the science world, it's becoming more enforced as a kind of religion. But the fact is that materialism is a reductionism. It's just saying, well, everything is nothing more than just atoms and empty space, or your, quark equivalent. But this process of science that I have up here, what I observe when I do it is that you can't do it without being a human being and without being open to things that are actually outside of the scope. So some form of integration, in other words, is inevitable. You're going to bring in ideas that are outside of science, so you might as well just face it and talk about it so that you can do it in a way that lets everybody be on the level playing field. So what do I mean? Well, when you do experiments, it's a very human process. What do you look at? Well, every scientist I've known, they are motivated by aesthetics. That doesn't mean that aesthetics answers any questions. It just means that when they choose problems, they say, I want to choose a really good problem. I want to find something that's really interesting, something that I find beautiful and amazing. And so, and it's getting harder and harder for them to get funding to do that, because the funding agencies want you to just generate something that's going to impact the economy. But the best scientists that I've known are motivated by the fact that it's really interesting and beautiful. And that's not something that reductionism helps you understand. And then you have to come up with a theory, but how do you know what to look at? Even if you know, any physical phenomenon, there's a lot going on at the same time. So how do you know what to focus on? And this is what students eventually learn as they are disciplined to do science. They learn, okay, just look at this, just look at that. But the truth is, we don't always know what we should be looking at, and we don't even always, and we don't know what often the questions are that we should ask. And that's really a lot of science, is finally figuring out what the questions are that we should be asking. That's not something, that's metaphysics. That's going outside of anything that you can't, measure these concepts. Now, you can make measurements and then you form an idea. But here's the real thing that all the great scientists that, for instance, Einstein considered it a miracle. Why is anything intelligible to us? Why can our little brains make sense out of anything? It's really amazing. It's amazing that we can actually get somewhere. Because when you look at the universe, it's very complicated. And you might think, yes, okay, maybe there is a theory, but we wouldn't understand it anyway. And for many centuries, great civilizations on the planet Earth, people didn't explore science because they thought we'll never get anywhere. And it was really Christian faith, I think, from my reading of history, that played a role in this. And I think, I'll mention a few of the individuals who really impacted me. But this picture, I observe so I now have grandchildren, and if you ever watch a toddler learn, this is not just how scientists function. This is how all human beings learn. Look at a toddler. They're doing science very fast. They're trying things, forming ideas, testing their theory, put my hand on this, oh, it's hot, boom, just learned something there, and you see them walking, figuring out, actually walking is a complicated process, and they just, through trial and error, forming ideas, testing them, they figure it out. And so I think that, and I've looked at some of the literature on acquisition of knowledge with children, and it's a scientific process. So I think it's not just people with lab coats that learn this way. I think this is how everyone does. And so I've often had people say, well, I would never be able to ask a good question of scientists. I'm like, try me. I bet you your question's good because you're a human being. And this is how human beings learn. We try ideas, we test them, and we're actually able to get somewhere amazingly. And then on the other side of this, once you've got an idea with a theory, and if it's intelligible, then application, you have to live it. And so for me, as I came to faith through reading the Bible, and as I tried to struggle with that, I started realizing, well, unless it's lived, it's nothing. And so, in other words, I realized this not only applied to my science, it applied to my Christian faith, right? The same process of learning, of interacting. And one final thing, there's a lot that, you see, it goes around in a circle. You do an experiment, you come up with an idea, you refine it into a theory, you test it, and usually what happens is you got somewhere, but if you look closely, it doesn't explain everything. So then you go back and you do another experiment. Now the thing is, philosophers have never been able to prove that you won't just keep going round and round and round and never really getting anywhere. But experience shows that you do get somewhere. And that has no explanation in a priori, philosophy. For me, it's a question of faith. Every time I have a graduate student who comes in and wants to work in my lab, they're like, all these bright physicists have come before me. How can I possibly, discover anything? And I'm like, work hard, do your work, and you will, on the shoulders of everybody who came before you, you will, by faith, you will be able to add something. You'll be able to get a PhD. You'll be able to do something that nobody has done before. It may not be, earth-shattering, but it will be something that adds to what's come before in a meaningful way. Now, one of the things that I've come up against as I did this, I had classmates who say, you can't be, and I even had a faculty member tell me this not too long ago. He said, you can't be a scientist and a Christian. You can't. He said, you have to be an atheist. Unless you're an atheist, you can't be a scientist. This was a professor of religion at Iowa State who said that to me. And I thought, well, that's not true in any way I can understand. I know I have friends who are Hindus and scientists. I have friends who are, of every religion, and they're scientists. And so how can you tell me you have to be an atheist? But the thing is that, just so you know, many of the people who popularize science are kind of evangelizing a religion which is Epicurean materialism. I just quoted this quote, which came from I guess you can't see who it's from. It's Michael Shermer, Scientific American, 2002. So this is, a major journal for popularizing science to the public. And what he's saying is, that scientism is a scientific worldview. In fact, at least he's using a separate word, scientism. My colleague at Iowa State just said, no, science is a worldview which is reductionism completely. So in other words, to be a scientist, you have to be an atheist because you have to believe that there's nothing that exists or is real except for atoms and empty space. And Shermer is saying that we should worship our scientists because they're the shamans of this new religion. But so I have gone further back in history. Now, I do have heroes in the scientific world, and one of them is James Clerk Maxwell. And when I read Maxwell, and he was, so in case you don't know, he basically understood and put together electromagnetic theory, realized that electricity and magnetism were connected in a deep way, and it came up with a theory of understanding how light propagates. It gave us a wave equation for light. So a major advance. And in fact, Einstein, when he visited England, they said, would you like the Newton chair of physics? He said, no, I want Maxwell. Because he actually, if you study Einstein, you'll realize that a lot of his way of thinking and his approach is built on Maxwell. Well, Maxwell was a Christian. And there are two things here I'll mention. One is that in our day and age, I think the balance of that cycle is tilted toward theory. So everybody thinks that theory is everything. And the experimenters just go behind them and prove that they were right all along. As an experimental scientist, I don't really subscribe to that. And I sort of agree with Maxwell here, who says, I have no reason to believe that human intellect is able to weave a system of physics out of its own resources without experiments. Whenever the attempt is made, it's resulted in unnatural and self-contradictory mass of rubbish, which is sort of a pithy way to say something. But the fact is that I think it's the glory of God that the universe is on the one hand intelligible, on the other hand, you can have 10,000 people, really smart people working full time, making progress and not getting to the end of it. Isn't that amazing? You might think, physics would either be impossible and you'd never get anywhere, or you'd finish it in a couple of weeks, But no, it's this very amazing thing filled with surprises, twists, and turns. And Maxwell describes it here. He said, and so here you see his Christian faith coming out. He said, we look down into these unsearchable depths and treasure up with care what with our little line and plummet we can reach. In other words, he's admitting our minds you wouldn't think we'd get anywhere. But he says we ought to admire the wisdom of him who has so arranged these mysteries that we can find first that which we can understand at first and the rest in order. So it's possible for us to build up an ever-increasing stock of known things about nature which is really fundamentally beyond us, right? It's really an amazing statement. But the truth is, if the only way we could have understood light was with quantum field theory, and no other theory got you anywhere, we would have never gotten there. Instead, we have theories of light. Newton had a theory that it was particles, and then went to a wave theory, and then there was quantum theory, and then in other words, the universe is laid out in such a way that we can learn it. And you get an unmistakable sense that someone just laid it out there so that we could discover it and make it really interesting. And it's hard, but you don't ever get jammed so that you never make any progress. This is an amazing fact about just the way the world is. But there's another interesting thing. If you think that the universe is just all about reducing everything to mathematics, and that's what people do nowadays, largely in my field, want to reduce everything, find what they call a theory of everything, which would be a mathematical theory, which explains absolutely everything. There's a problem with that. And this is something which I'll just give you my own sort of personal, again, it's a very personal story. I was in England, and I wanted to see this Rosetta Stone. Now, if you know about the Rosetta Stone, it's an interesting archaeological artifact here because it has hieroglyphics and it has some other ancient languages written on it. And so if we didn't have the Rosetta Stone, no one would have been able to figure out what hieroglyphics meant because there were no longer people around who wrote hieroglyphics, and no one knew. Now, even though the hieroglyphics are pictures, you might think, oh, that little blue thing there means a blue jay. It doesn't mean blue jay, okay? It looks like a blue jay, but it isn't. In other words, they are forms, they're images, but their meaning. Now, how would you find out the meaning of hieroglyphics? Well, if science tells you the meaning of everything, we just take that stone, take it down to the chem lab, and do tests on it, and we'll determine the meaning of everything, right? Well, the truth is, of course, that won't get you anywhere. If you determine the properties of rock, because what's interesting about the hieroglyphics, it doesn't really have anything to do with rock, right? Yeah, sure, it's on the rock, and there are forms, but those forms don't dictate what the meaning is. So here I'll give you a simple explanation, or a simple example. Consider a square, right? Now that's something you know from geometry. And so what's the meaning of this square? Well, you could say, well, the answer would be found by geometry, right? I mean, that's the theory of these forms. Well, geometry tells you, you've got four sides, and they've got to be equal, and it's got four angles, and they're all 90-degree angles, and is that what it means? Is that all there is to say about it? Because this is what people are doing in physics. They'll just study something and take it into, subatomic particles and say, that's the fundamental meaning of the universe. But does that even make sense? Well, it turns out that a square, it's actually a letter in the Japanese alphabet. And it also has meaning in art. So, a square, here's if you ever see a fresco like this, so you see the square, and what that means is that individual was not only considered a saint, he was living at the time they did the artwork. So the square has that extra meaning, which you can't determine from any kind of scientific analysis of this art. And so, what does that mean? It means that integration is absolutely essential. Whenever a scientist gets up and wants to talk about their theory, right? Well, yes, you do need to know the form. So science is always involved in the quest for meaning at some level. You have to understand the shape of what things are. But the math or the science does not determine its meaning. It only determines its form, like it's a square. However, Everybody who communicates science, especially to the public, always talks about what it means. I've never, at any scientific conference, ever heard a scientist say, okay, here's this equation, and of course it's completely meaningless. My theory is meaningless. No, they never say that, right? It's always clothed in meaning. And where did that meaning come from? Well, it didn't come from the laboratory, so it came from their worldview. And so when Michael Shermer talks about scientism being a worldview, he's talking about reductionism. He's talking about the religion of what's really Epicurean materialism. So if you go back to Epicurus, you'll see what a description of what is now being sold to the public, often as science itself. So the semantic interpretation, in other words, the meaning dimension of things, does not come from science. It comes from outside of science. Yet science can't even function, I would argue. It's not just it's kind of nice to clothe it in meaning. Science doesn't even function without the semantic dimension and the ethical dimension. As department chair in physics and astronomy, I was required by the National Science Foundation to run an ethics lecture. And why? Because people realize you want scientists to tell the truth. You want scientists to treat their students correctly. There are all kinds of things. And to tell you the truth, if you don't do those things, if you don't tell the truth, if you don't treat people well, science doesn't function. It's a human community, right? Even Einstein, he wasn't a Lone Ranger. He was plugged into a scientific community which are human beings relating to one another. And so you can't even do science without getting into questions that go beyond what science is. If you want to say science is just this production of mathematical forms. And so under materialism, so I knew Steven Weinberg, he was a great physicist in the 20th century, but he was a materialist, and his statement here is that what he's saying is that the more the universe seems comprehensible, the more it also seems pointless. And what he means is the more you reduce it down to a simple equation, you say, well, what was the point? Right? So, yes, the materialism, I consider it kind of a degenerate philosophy because it undermines, not only is science meaningless, everything's meaningless under materialism. Everything. Language. So, this has just been, I'm leading through my own personal, sort of trajectory through this and struggle with trying to understand how then you live as a human being doing science and in a way that is honest and which gives you a foundation for dealing with the ethical questions which are real and which you cannot ignore. So so now back to the Aurora. So the interesting thing is that, in science you just measure things. Yes, you can start in very simple ways, and then you plot them. Now this plot here would be kind of disappointing because the data points are all over the page. And there are several ways to be wrong in science. In fact, there are an infinite number of ways of being wrong in science, I think. An uncountable infinity of ways of being wrong. But there are two classes of ways of being wrong. One is what are called random errors, which means you didn't make a precise enough measurement, and so every time you do it, you get a different answer. And that we can measure, and we can use statistics, and that's helpful. But there's a more profound way to be wrong, and that is what we call a systematic error. And that means that something in your thinking is wrong. You don't know what. It could be what you think you're measuring that's wrong. It could be what you think your measurement instruments are doing is wrong. It could be the whole concept. The categories you've chosen, the questions you're asking don't correspond to reality. And this could have been, like the fate of mankind. We looked around and we never could make sense out of anything. It's just scattered points. But here's something, and AJ will like this, as he's an expert on stars. This is a Hubble picture, and growing up in the country, you look up in the sky and you really see the stars, and you realize they're different colors, and they're different brightnesses, and there are a lot of them. And so that's this picture. And now you could say, let me try something obvious. Let me just make a plot like that XY plot, and I'll put color on one axis and brightness on the other axis. And you might think, well, you just have a graph like this, right? I'll pop things all over the place, but actually, it doesn't. I don't have time to talk about this graph. I have to ask AJ, actually. He's our resident expert. But the fact is, when you try things like this, you say, hey, we're onto something. And now you've got a research program. Now you can say, well, I wonder why it's there and not somewhere else, right? I wonder why it looks like this when it could have been, well, you'd think anything. So now back to the aurora. There are many kinds of aurora, and the kind of aurora I wanted to help understand was the kind on the left where they're filaments, and they happen in certain kind of storm. Let's see if this runs automatically or if I probably have to start it. Explosions happen on the sun. You see that our force field is protecting the planet. And then the magnetic field of the Earth gets squashed. And there's a very interesting process called magnetic reconnection that happens. And it somehow propels particles into the Earth's atmosphere. And I went on the web just to see what kinds of things are out there. And yes, you have electric charged particles coming down into the atmosphere, banging into atoms and making colors. And there's oxygen, which is red, nitrogen, which does produce blue and red colors, and green. Now, I've never heard anybody who works on these auroras talk about this, but it's very interesting to me from an artistic point of view. And that is, I looked on the web and I said, what kind of colors come with auroras? And there were various things, and there was questions that people ask and then answers. And one person said, why do I see white light? And the answer to that was magic. And I'm like, what do you mean magic? And now the reason they gave was scientifically valid at a certain level. They said, well, but because all these gases only give pure spectral colors, and white is not a pure spectral color, so you can't have it. Well, since I taught myself how to repair TVs back in the 60s, and color TV eventually came out, I'm aware of a thing called a chromaticity diagram, and people who do art are aware of this too. All the colors that a person can see are in this, and that's because you have in your eye three kinds of, a trinity of detectors. And so there are kind of fundamental colors in from which you can construct other colors. Now the perimeter of there, you can see, is marked with numbers ranging from 380 down to 700. Those are wavelengths in nanometers. But the fact is that the pure spectral colors produced by those atoms in the atmosphere are all right along the perimeter, the top perimeter. Now in the video, the NASA video, she said, and some produce purple light. Well, there is no purple photon, okay? The photons are red, orange, yellow, green, blue, indigo, violet. But for your brain, purple is a fundamental color, right? And it's along the bottom edge there. And so the way you get purple is red and blue. Now the thing is, those atoms I mentioned, the oxygen and nitrogen, they produce the primary colors, so you can make any color there is in an aurora, right? I've never heard people discuss that, including if you see the white spot in the middle, that's called the white point, and it turns out there's an infinite number of ways of making white. I'm just add a little bit of extra science for you, just to, no extra cost. So you can make white by adding two colors that are opposites to each other, diametrically on the perimeter, but opposite from the white point. So in other words, all it takes is two spectral colors and you can get white. And so and that's what's happening in the Aurora when you do, because if you look at the videos, you do see white, all right? It's not magic. All right. So why mention this? Well, we talk about the beauty of it. Just so happens that in addition to protecting the planet, and in addition to being an interesting physics laboratory, the Aurora is beautiful and can make any color you can imagine for the human eye, which is interesting. So it's just a little movie of the. So, first of all, what was the backdrop? Well, space scientists had flown spacecraft. So there's one that was called the polar spacecraft. And it goes over the poles. And what did they see? They saw another one called the FAST satellite. And they looked and they saw that there were, first you see on the left there, snapshot of the Aurora taken from space. You can see that ring of color, or it's not ring of light. Not a lot of color in that picture. Then the next one is if you just take a lot of those and average them, you see that mostly, if you want to see auroras, you have to be at a certain location on the Earth around the pole. And there's also a ring around the southern pole. And don't worry about the Alfvén wave I'll just give you a quick lesson on that. The magnetic field of the Earth is a little bit like a guitar string. And if you pluck it, the wave is a transverse wave that travels along the magnetic field, and that is an Alfvén wave. And this is the wave that we thought seems to be correlated here, they said, in the space physics literature, and our job was to see, could we do this in the lab? So the idea is that these waves would be launched from the tail, what's called the magnetotail, the opposite side of the Earth from the sun, and come back up along the magnetic field, as shown in the little video there, and produce the Aurora. How would this do it? Imagine you had a little ring on a rope, and if you whip that rope just right, you would be able to propel the ring down the rope. Or, what I'm showing here is a wave coming along, and there's a surfer, and the wave ends up pushing the surfer and propelling them. The idea was that the magnetic field is producing their waves, which just like pushing the surfer, they're pushing electric current down in and lighting up the atmosphere like a gigantic fluorescent light bulb. And so how do we look at this in the lab? Well, the plasma has this in common with gases. You've got particles going all over the place. And so I have spent many years measuring these, how fast, how many particles are going how fast, and building up a table, which is called a distribution. And by measuring that distribution, you know how many particles are going at what speeds. So now what happens is, what if there's a wave going and the wave is causing the surfers, like that little red ball, to be accelerated off to the right-hand side? It will modify this distribution on the left. Don't worry about it, there's no quiz at the end. So but the idea was, and so my space physics colleagues came to me and said, yeah, we want to measure a very small part of a very small part of the electrons that are going on, and they actually are responsible for all the light. So 1 part in a million, and then I want 1 part of the million of that. And nobody knows how to measure that. So that was where I got involved. We had this big machine out at UCLA, which is, say, 20 meters long, so each meter is like 3 feet. So it's a big machine, much bigger than the one we have at Iowa. And we would launch these waves, when shown sort of schematically in blue there. And then my job was to try to figure out how can we measure those electrons which are surfing on the wave, which end up getting energy from the wave, and then could drive something like an aurora. Well, first I had to build a probe that could measure the guitar string vibrating. So I said the Alfvén wave is like a plucked guitar string. In this big machine, we had magnetic fields, and we plucked them, found a way to pluck them, and measure them. This is a picture of all the guitar strings vibrating. And we had a nice, lined up in nice straight rows, but that's a picture of an Alfvén wave after Hannes Alfvén, who was the one who discovered this kind of wave that exists all over the place in space. And then I had to invent a contraption, and I will not take your time now to explain this contraption, but basically, this is a contraption which enabled me to measure 1/millionth of 1/millionth of the electrons and how many of them there are. And I put it in that device at UCLA. And so this actually was the first part of the measurement, which just is, they made their plasma, it's a little bit like an aurora plasma in a way, because they push electric current through the entire gas, just like what's happening, and it lights up like a gigantic fluorescent light bulb. And I could measure that in one direction, there were a lot more electrons going than in the other direction. That's what that plot means. On the left, there's a lot more electrons, and that was the current. But then that wasn't what they wanted to see. What they wanted to see is on the other side, a very small number of electrons which somehow are getting accelerated. Well, to make a long story short, after a lot of work, we saw this little bump. Now, most of you say, is that worth 3 years of work? But we were very excited about it. And that's what it takes. It takes, to be a scientist, you have to be astounded at what most people don't even think there's something there. I'm always astounded when science works, because you spend so much time with things breaking that when everything works and you get a good measurement, and it actually agrees with theory, that your limited understanding. So that little bump on the right-hand side was confirmation of the mechanism of how the aurora drives electric current that lights up in certain kinds of aurora, not all auroras. In fact, my student, Jim Schroeder, he's now a professor of physics at Wheaton, he was very careful in talking to the media, but the media did kind of over-exaggerate, what we had done. The fact is, we did do something, and just like all science, basically, we just took it one other step. We advanced made a measurement that nobody had ever made before, and added to what was there, and now we understand things a little bit better, but there's still a lot more to know. Still a lot more that it would be nice to understand. Well, there are aurora at other planets, and at the University of Iowa, actually, we're doing a lot with Mars right now. But Mars has auroras, even though it doesn't have a magnetic field. And it would appear that the particular way auroras work, are related to how our planet has kept its atmosphere. And I don't know about you, but I'm really glad that we have air to breathe, and it doesn't just blow off into space. And so, again, it's not only beautiful, it's not only interesting, it's providential. So I will end my talk with one. So when I was on sabbatical in, did I kick out here? In France, and when I lived in Switzerland, I had to communicate in French and teach in French. I found a book in a little library that was Ampere's poems. Ampere was another scientist, Christian, in the 19th century. And I produced, which I I think it's the first translation of this poem of his. And it was called The True Scientist. Happy the one who in his learned watches, contemplating the marvels of this vast universe, before so much beauty, before so much grandeur, bows the knee and acknowledges the divine creator. I do not share the foolish incoherence of the scientist who would contest the existence of God, who would close his ears to what the heavens declare, and refuse to see what shines before his eyes. To know God, to love him, and to offer him a pure homage, that is true knowledge and the study of the wise. So I can't think of a better way to end my presentation, but with that. So this has sort of been my own personal journey, and I'm happy to take questions.
Thank you, Fred, for your inspiring talk. There's time for questions right now. Andrew and Casey have mics right there. If you have a question, raise your hand. We have about 15 minutes or so for Q&A.
Thank you, Dr. Skiff, for your wonderful lecture. It seems ultimately it was what's driving your conviction that there is purpose behind this. It seemed you were talking about you're looking for meaning, and is it an internal? Do you think it's an internal driving that you have, that you're looking for meaning and purpose, that you don't want to live in a world that lacks meaning and purpose? Is that what is driving this, or do you see evidences in what you have studied and in your scientific studies? So, how much of it is external? How much of this is internal in your own analysis of how you put your faith and your field together?
I mean, my study of science has really affected me, and also my Christian faith is, so it's all integrated together. But I think that, I've never met a scientist who thought the world was meaningless. And actually, I've had some of my astronomy colleagues tell me, Fred, when you look through a telescope, there's nobody who's an atheist. I don't know if that's true. I'm sure there are atheists who look through telescopes, but the fact is that it's very moving. And so I think there's a shared, I think that the heavens do declare the glory of God, and the skies do proclaim the work of his hands. And day after day they display, they put forth speech. Night after night they display knowledge. And I think that in a sense that it was laid out for us, and even with our small minds, we're able to get somewhere. We're able to actually slowly unravel things that we thought would never be understood, right? Yet there's so much more that we don't understand. And so that kind of, but of course, you're talking to a human who's saying that's my experience of, studying science, is that it really suggests to me that there is a meaning, there is purpose behind it all, and there are these miraculous things. There are, things that if, so as I was involved in the fusion program, and I remember there was a big thing in 1989 about cold fusion. And I was looking at, because we all had to look at it and try to figure out what on earth's going on here. And one thing that became clear, if Planck's constant were slightly different, you'd sit on a chair and you'd have a thermonuclear explosion. That would be bad, It's so, and it's, because it's in the exponent of a thing, it's very sensitive. And so now we have this world filled with such richness. But if you, as a kind of homework problem, try to work out your own universe, well, maybe it contains one neutron, and it's just not going to be a very interesting universe. And it's, in order to get the kind of richness, the kind of beauty that we see, things have to be a certain way and not, another way. And after a while looking, it's like, it just doesn't make sense that it would happen for no reason. you know? And so I continue to affirm what I thought as a little kid. You know, when I looked at the apple tree and the tadpole and thought, I don't think that's just a random thing, you know. I think that was a correct assessment.
I have a question about whether you consider phenomena when they're more hi.
Yeah, no, I'm hard of hearing, so that's what I'm making sure I can hear it.
Do you consider phenomena to be more beautiful when they're mysterious, when we don't understand them? Or are they more beautiful when we do understand them? And I'm interested in particular in the case you mentioned very, very briefly at the end about auroras in the case of Mars, yet Mars doesn't have an appreciable atmosphere or magnetic fields that provide the mechanism for auroras on Earth. That seems mysterious to me, but
Yeah.
does it make it more beautiful or less beautiful to you?
You know, I mean, the whole idea of aesthetics is complicated and very human. Some things are learned, right? And some things seem to everybody seems to, you know. I taught for many years a course on the physics of sound. And what sounds dissonant and unpleasant and things, there are physiological reasons. I didn't fully explain it, but music is something very human, right? And so our aesthetics is built into who we are. And so, I mean, I agree with Paul Dirac, you know, when he talked about the beauty of his mathematics. But can we quantify that? Can we say, like, when you try to get too precise about it, it's very hard to do that. But I do say that there is a kind of beauty in slightly broken symmetry, which is a lot of what the universe contains. Even in human faces, if they're, you know, I mean, no face is perfectly symmetrical. And that's part of the character, part of the beauty of it. And so I think it's not simply geometrical exactness or something, you know. It's not just that. So, yeah, I think we may have a roundtable discussion tomorrow to talk about this. It's a very interesting subject and not one that, you know, I don't have any formal art training, so but I as a human being, I do have an appreciation of beauty, just like anyone else. Yeah.
You described how the Earth's magnetic field is like a force field protecting us from all the particles from the sun. Should we be concerned the next time the magnetic poles flip in the Earth?
Yeah, I think the time scales, as far as we know, the time scales for where trouble would happen are long enough that, and the flip happens, not instantaneously, but it would appear to be, you know, relatively quick, that we shouldn't, you know, I don't think that we would instantly lose our atmosphere. That's the best of, you know, the knowledge right now, is that it's not something you should, you know, fear. But certainly there would be environmental impacts, you know, and weather impacts. I mean, from what we understand, there are, you know, everything's interconnected. And I don't think we understand fully, you know, all the impacts. But, you know, these are active areas of research that people are trying to sort out, and they're very complicated. So, but I don't believe that it's something where you would instantly lose the atmosphere. But it might start eroding, you know, and more, and then certainly you would expect the erosion to be different. And so, you know, that's one of the reasons that space physics is important, to try to understand our environment. You know, what should we expect, and what, you know. So that's I looked into this some, and of course that's not, you know, it's not really my specialty, but you know, the whole area of atmospheric loss. But it's clear that the force field does protect the planet, you know, from high energy particles, and certainly for you and me, I mean, we are subject to radiation from space, and the magnetic field protects us from a lot of that. So you would get a higher dose, you know, and for example, if a major solar explosion happened during the Apollo missions, it would have killed all the astronauts. Because when you get out to the moon, you're largely exposed. You're largely not protected by the magnetosphere. And it would have been enough dose to kill them. So so there's clearly between that and, so if you had, a lot of solar activity and no shielding, you'd certainly be getting more dose.
You were mentioning that in 1967 you saw like a really strong Aurora show. Like, what kind of impact did that make? Was seeing that the thing that made you want to study like plasmas?
Well, it certainly, it impacted my interest in science. I mean, I had a lot of factors that influenced my interest. I mean, initially I didn't think I was smart enough to be a scientist. And, it was only when I got to Cornell, and then I was, on the top student in college, then I realized, oh, maybe I can do this. But, I went to a little tiny high school in the middle of nowhere and never had calculus before, so I didn't, I kind of wanted to, but I thought I didn't think I could. But then I was able to. I really just considered God's providence that I've been able to, it's a blessing when you find something you can do. But yes, I mean, I was fascinated by everything, There's so much in the world so I think I was destined to be a scientist in that sense. I mean, there are a lot of things that everybody, the sun rises and sets, and people just sort of don't think about it, or they look in the sky. But for me, I was just astounded at what was going on, And so, yeah, that event really did impress me. I mean, I was I didn't know if the world was ending or what. I was just a little 10-year-old kid seeing this huge light show in the sky, and I had no idea what it was. So it definitely had a huge impact on me, but there are many things about the world that I really wanted to understand.
Thank you for your presentation today, and congratulations on your discovery. Do you think there will be practical applications for your discovery, particularly when it comes to GPS and the delays that occur at low latitudes from anomalies in the ionosphere driven by space weather, like scintillation and bubble gradients?
So our research, ties in to trying to understand. So NASA has a program in heliophysics, and so that's everything from the sun to the earth. And yes, I mean, everyone's concerned about, understanding space weather. So because our satellites can get destroyed with solar events, storms can disrupt but our work was really, so what we did is we dug deep at a certain question, like, what's the mechanism? And that answers a very specific question. Then when you want to understand some of these other things you're mentioning, you've got to bring in a whole bunch of factors, and it's only one small piece of that, right? And so that's the way science is. There's some people who write a computer code where they put all the microphysics that people have been hammering out into one thing and say, okay, now can we understand what's going on here? And then there are people who, like me, who are saying, okay, do we understand this mechanism? Let's make an experiment, very controlled, and just answer a very simple, because that's what it takes to really get your feet on the ground, is you make it so that you really only have one possible answer to this question, When you have too many possible answers, then you're always left guessing.
My question is not specifically about plasma. It's it's from cosmology. And so with the Webb telescope, are there, would you know, any surprises that from the Webb telescope that may lead to some kind of paradigm shift?
Well, yes, I mean, I think these things are going to, there are lots of things that are not understood. You know, there are lots of new data. And so, if you were to ask me as a physicist where I actually, I mean, the Webb telescope the new instruments that are coming online are definitely coming up with things that nobody knows what they are. And so what's happening around, there are some very exotic stars. There are certain places in the universe where the laws of physics as we know it may be breaking down, right? Or because we can't build an experiment to test, for example, the interface between quantum mechanics and general relativity. But if you get really good images, say, around a black hole, right, of the region, just around it. I mean, Hawking's theory is kind of a kludge. I mean, he basically, it was the best anybody could do, but it basically is not a quantum gravity. It's kind of patching things together. And so it's possible that when we get good measurements, we'll say, wait a minute, this doesn't work. This is not adding up, right? And then that would cause, and also whenever you have, so plasma is most of what we see. But of course, right now, if you ask, cosmologists, well, we have dark energy and dark matter. What are they? Well, we don't know, right? So, I mean, I think we're set up, I think that, a student entering now, it's a pretty exciting time because our technology has improved to the point where we can really make some really nice measurements. And it's likely whenever you have a lot of things like, well, most of the universe is made of, well, I don't know. Well, okay, so that means we're set up for some really interesting, times, I think. So, yeah, I try to encourage students. In no way, shape, or form is science done, And that's interesting, like my hero, Maxwell. Most physicists in the 19th century thought they were done. Like we have Newton mechanics, we have an answer for everything. And my two heroes, Faraday, who was, I think, the best experimental scientist of all time, and Maxwell, both said, no, I don't think so.
Perhaps one more question? You just mentioned Michael Faraday, and I'm
Yes.
not a scientist, but I'm curious. I know that when he developed his theory of electromagnetism, he was mocked for it. He's a Christian, and he's there, and they kind of were making fun of him, invisible fields and all that kind of thing. Are you able to elaborate on that, why it was controversial and why they mocked him in such a way?
Yeah, I have on my webpage, I have my favorite quotes. This is one of my web pages, of course, has my translation of Ampere's poem. But one of my favorite quotes, I have his researches, really just an amazing thing. Someone who could understand electromagnetic theory without he didn't know calculus. He was just an extremely good thinker. And he was also a good exegete. I mean, he preached in his local church. And yes, in fact, the quote I'm thinking of, he says, I put forward the bold idea of anti-materialism. Okay? He knew that whatever an electromagnetic field is, it wasn't atoms, it wasn't empty space. And so he knew that he was in some ways coming to grips with a relativistic quantum field before anybody had any words to talk about it. He could see there was something going on here that was not fitting into people's idea of what can exist. Because materialism is always saying, oh, it's nothing but, nothing but, nothing but. You're nothing but atoms and empty space. It's all, your brain is nothing but chemical reaction, nothing but. And so that was very much prevalent in the 19th century, And so he put this forward like, no, there's stuff out there that just isn't going to fit into your little box. And he was right. He was onto a deep mystery. And I think that Faraday's law really, even for almost 100 years, was not really understood. There were a lot of the people who followed him were materialists and insisted that the ether has got to be some kind of jelly, an invisible jelly. The light travels through this material ether. And the question of the ether is strange because people sometimes take the experiments to have shown that there's no such thing as ether. That's not true either. You can't say that light is an excitation of something that doesn't exist, right? What it means is there's an ether. It's a quantum relativistic ether. I mean, there's something there. It's just weirder than you had in mind, you know? And so yeah, I mean, I think for him to have been able to grasp that with just his really good exegetical mind of like, let me just try to exegete nature. That was really what I think set Faraday apart. A lot of people would have a theory, and then they cherry pick things to prop up their theory. And Faraday's like, that's not how you exegete. You know, what you do is let the text tell you what it's saying, right? Only he was trying to do this with physical experiments, which is, I mean, that's why I consider him really anybody who can understand electromagnetic theory without calculus. I put that as a challenge. It's not easy to do. And he did it. And if you read his researches, it's really a masterpiece, really, I would say, of experimental science. So, but that's just, and it was very connected to his Christian faith. He had an integrated view.
Fred, thank you very much for this very personal lecture that you gave us tonight. I heard you this afternoon in the physics department, and it was a very theoretical, very thorough, of which I probably understood about 5%. But tonight you showed us on very different sides, and personal wrestling with science, trying to understand what science is, what the process of science is, how to make sense of different things, what actually is meaning underneath science, and all of that kind of interlaced with like some beautiful understanding and explanations of the Northern Lights, and how that shows some of the science and the meaning and the purpose that we see in the magnetic fields and in the creation of the universe and of the Earth itself. So thank you very much for showing us that science is beautiful, that science is wonderful as a human enterprise, and that we learn something about the universe that we cannot really understand in any other ways. If you want to talk a little bit more about that, we have a reception with some food right over there, right after this lecture, and you're welcome to hang around. Fred will be there, and I assume you will be open for some questions there as well. So if you have some more questions for Fred, join us for the reception afterwards. Thank you for coming tonight. And I would like to draw your attention to another lecture that we have in a couple of weeks, and that is the Holmer lecture. This was the Anderson lecture in Science and Religion. We also have the Holmer lecture in the Humanities and Christianity. And that lecture is a rescheduled lecture that was supposed to be early April, but there were some personal circumstances that made it impossible for that lecturer to come. But he is coming back on May 6th. So May 6th, from 7 till 8:30, here in McNamara again. And the lecturer is Carlos Eyre, Dr. Carlos Eyre. He's an historian from Yale. And he is going to talk about the history of the impossible. And the impossible is basically things that look miraculous to us. For example, flying saints, levitating saints, bilocating saints. And he has done a lot of, as an historian, he has done a lot of research on what do you do with those kind of like accounts that people have written down. And how do you kind of like interpret that? And so he is going to talk about the history of the impossible, talking about how do you make sense of like those kind of like events, and he's really trying to figure out like what is the boundary, so to say, between the natural and the supernatural. So very, very interesting. So you're very welcome to come to that lecture as well. May 6th here in McNamara, 7 till 8:30. If you want more information, go to our website, or we have a table right up there, and you can find flyers and all kind of other information about Anselm House there as well. I think that is mostly from me. Thank you very much for being here tonight, and thank you, Fred, for being here tonight as well, and for sharing your story and your heart with us.